Hello everyone, and welcome to the SysGuides YouTube channel. In this video, I will guide you through the process of installing Fedora 42 Workstation with full disk encryption using LUKS, along with snapshot and rollback support using Btrfs and Snapper. This setup adds a strong layer of security and reliability to your system. If something goes wrong, like a bad update or a broken configuration, you will be able to roll back your system to a previous working state with just a few commands. Whether you are a Linux newbie or a seasoned user, this guide will help you create a secure and resilient Fedora setup. Here is a quick overview of what I will cover in this video. I've already downloaded the Fedora 42 ISO and created a bootable USB installer. Now let's move ahead and begin the installation process. Start by booting your computer from the Fedora Workstation 42 installer in UEFI mode. When the Welcome to Fedora window appears, click Not Now to skip the initial setup and return directly to the GNOME desktop environment. By default, the Anaconda Web UI installer doesn't support encrypting the boot partition, which is necessary for full disk encryption with LUKS. To enable this feature, we need to edit an internal configuration file used by the installer. So go ahead and open the terminal. We will make a quick change to a script to unlock full encryption support. First, switch to super user mode. Next, we will use nano with line numbers enabled to open a Python script named base.py, which is located deep within the /usr/lib64 directory structure. Now we need to jump directly to line 183 to make a small edit. To do that in nano, press Ctrl+Shift+_, then type 183 and hit Enter. Now change the encryption support value from false to true. This change enables support for boot encryption during installation, which is otherwise disabled by default. Once done, save the file by pressing Ctrl+O, then press Enter. Exit nano by pressing Ctrl+X. With boot encryption support now enabled, go ahead and launch the Anaconda Web UI installer. Keep the terminal window open. We will come back to it after the installation is complete. The redesigned Anaconda Web UI should now appear. It offers a modern and streamlined experience, and as of Fedora 42, it's available only in the Workstation edition. Start by selecting your preferred language and keyboard layout. I will stick with the default options here. Click Next to continue. On the installation method screen, you will configure how Fedora will be installed. This includes selecting your target disk and setting up partitions. Make sure the correct installation disk is selected under the Destination section. In this demonstration, I am using a 128 GB virtual disk, which appears as VDA, corresponding to the device /dev/VDA. If the disk listed isn't the one you want to use, click Change Destination and select the appropriate drive. Since I'm working in a virtual machine with only one disk, the installer automatically selects /dev/VDA. If you have multiple disks, they'll all be listed here. You might notice the disk is shown as 137 gigabytes instead of 128 GB. That's because the installer uses gigabytes while Linux typically uses GB, and 128 GB roughly equals 137 gigabytes. By default, the installer offers the Use Entire Disk option, but we want a custom layout to manually configure partitions. So click the three-dot menu in the top right corner and select Launch Storage Editor. A warning will appear informing you that the storage editor is an advanced tool and that any changes you make are applied immediately. Don't worry, just click Launch Storage Editor to proceed. Inside the storage editor, we will begin by creating a new partition table. Be aware that this action will erase all existing partitions on the selected disk. If you are dual booting or have important data on this drive, make sure to back it up before proceeding. Since I am working with a blank disk, I will go ahead and click Create Partition Table. Next, we need to create the necessary partitions for our Fedora installation. Click the three-dot menu, then choose Create Partition. We will start with the EFI system partition. Set the size to 1.074 gigabytes, which is approximately 1 GB. Choose EFI system partition as the type. The mount point /boot/EFI will be filled in automatically. I will name this partition ESP, though you can name it anything you like. Click Create to finish creating the EFI partition. Now let us create the main partition for our system using the remaining free space. Once again, open the three-dot menu and select Create Partition. Label this partition Fedora or any name you like. Leave the mount point field empty. Set the file system type to Btrfs. We will use all remaining free space for this partition. Under the encryption settings, select LUKS2 as the encryption type. Then set a strong passphrase to secure the encrypted volume. Click Create to finalize the encrypted Btrfs partition. As you can see, the Btrfs file system is now encrypted. These are the only two partitions we need for this setup. I won't create a separate boot partition. Instead, I want the kernel and init RAM fs to reside inside the Btrfs root subvolume. This ensures that if I roll back the system, the kernel and init RAM fs are rolled back as well. This setup helps avoid mismatches between boot files and system files, which could otherwise lead to boot issues after a rollback. Also, there is no need to create a separate swap partition. Fedora automatically enables swap on ZRAM at boot. ZRAM creates a compressed block device in memory and uses it as swap space. This results in faster performance compared to traditional disk-based swap, and it also reduces wear on SSDs. ZRAM swap is created dynamically at startup and removed at shutdown. Now that we have created both required partitions, the EFI system partition and the encrypted Btrfs partition, we are ready to create subvolumes inside the Btrfs volume. To do this, look for the line labeled Top Level and click the three-dot menu next to it and choose Create Subvolume. When setting up a system with snapshot and rollback support, it's important to create separate subvolumes for certain directories. This allows you to control what gets included or excluded during a snapshot and rollback. For example, you typically want to roll back system files, but not user data, logs, or cache files, which change frequently and could cause problems if rolled back. Isolating these directories into separate subvolumes helps maintain system stability and integrity during rollbacks. First, I'll create a subvolume for the root file system. This is where Fedora itself will be installed. It's the main subvolume, and it will be snapshot enabled so we can roll back the entire system if needed. I'll name this subvolume root and set its mount point as /, which represents the root of the file system. Next, I'll create a subvolume for home. This directory contains user data, personal files, and user-specific configuration files. By separating home, you can preserve your personal data even when rolling back the system. This subvolume will also be snapshot enabled. I'll name this subvolume home and mount it at /home. Next, I'll create a subvolume for OPT. This directory is often used for installing third-party applications and software that are not managed by the system package manager. Separating /opt ensures that if you roll back the system, your manually installed software remains unaffected. Now I'll create a subvolume for cache. This directory stores cache files such as downloaded packages and temporary data. Since cache data is constantly changing and not critical for a system rollback, isolating /var/cache prevents it from cluttering snapshots with unnecessary data. Next, I'll create a subvolume for GDM. This directory contains important files used by the GNOME Display Manager. Without separating it, Fedora Workstation can hang or fail to reach the login screen when booting into a read-only snapshot. Creating a separate subvolume here ensures smooth operation even when working with snapshots. Now, I'll create a subvolume for libvirt. If you use KVM virtualization, this directory holds your virtual machines and their settings. Separating it ensures that VM files remain stable and are not unintentionally reverted or corrupted during a system rollback. Next, I'll create a subvolume for log. Logs are frequently written and updated, and including them in snapshots could cause conflicts or fill up snapshot space quickly. By isolating /var/log, we avoid unnecessary snapshot bloat and potential issues when rolling back. Now I'll create a subvolume for spool. This directory is used by various services for temporary storage, like print queues and mail spools. Similar to logs, these files are transient and should not be rolled back with the system, so it's best to keep them separate. Finally, I'll create a subvolume for TMP. This directory holds temporary files that may persist across reboots, but are not critical. Keeping /var/tmp separate ensures that temporary files don't interfere with system snapshots and rollbacks. We've finished creating all the partitions and subvolumes needed for installing Fedora with snapshot and rollback support. Now click the Return to Installation button to head back to the main installation screen. If everything was set up correctly, you should see a green checkmark indicating a valid storage layout. Now press Continue. Click Next to review your installation summary. And finally, click the Install button to start the Fedora installation. The installation of Fedora Workstation 42 will now begin. The installation is now complete. Click the Exit to Live Desktop button to leave the Fedora installer. Please do not reboot your system yet. Instead, return to the terminal window to complete a few important post-installation steps. Your Fedora installation is currently mounted at /nnt/sysroot. Next, list all block devices. In my case, the installation disk is /dev/vda. Now, examine the partition and file system structure of this disk. You may recall that during the installation using the Anaconda installer, I chose LUKS version 2 instead of version 1 for full disk encryption. By default, the GRUB bootloader only supports encryption that uses the PBKDF2 key derivation function. This is the same method used by LUKS version 1, which is why most Linux distributions use LUKS 1 for full disk encryption. However, LUKS2 uses argon2id as the default key derivation function, and unfortunately, GRUB does not support argon2id. Therefore, in order to make the system bootable, we need to manually change the key derivation function from argon2id to pbkdf2. Now, you might wonder why I chose LUKS2 instead of the more GRUB-compatible LUKS1. The reason is that LUKS2, when used with PBKDF2, offers the same GRUB compatibility as LUKS1, but with a more modern and extensible encryption framework. LUKS2 provides better metadata handling, support for larger key sizes, improved recovery features, and enhanced flexibility for future cryptographic improvements. Even though GRUB does not yet support modern key derivation functions like argon2id, LUKS2's architecture makes it a better long-term choice for disk encryption, without sacrificing backward compatibility. Now let us check the current key derivation function in use. My encrypted root partition is located at /dev/vda2. As you can see, the current PBKDF is set to argon2 ID. We need to change this to PBKDF2 so that grub can unlock the disk at boot. To make this change, use the LUKS change key command. Set the PBKDF to PBKDF2 and specify an iteration count. In this example, I am setting the iteration count to 500,000. Please note that higher iteration counts will result in a longer unlock time during boot. I have chosen 500,000 here as a balanced example, but you can adjust this number depending on your system's performance. You will be prompted to enter your passphrase 3 times. The first prompt is for authentication, and the next 2 are for setting the new key. Do not change your passphrase. Simply enter the same one each time. After the command completes, verify the changes. As you can see, the PBKDF is now set to PBKDF2, and the iteration count has been updated to 500,000. Next, you need to enable crypto disk support and use the crypto mount command. These are essential for allowing grub, the bootloader, to unlock your encrypted drive during boot. Without this step, grub would not be able to read the encrypted volume and load Fedora. Let us begin by adding the crypto mount command to the grub configuration. First, you will need the UUID of your encrypted root partition. In my case, that partition is /dev/vda2, which uses LUKS2 encryption and is identified as crypto-LUKS. Copy the UUID of the encrypted partition. Now open the grub configuration file located inside the EFI directory of your installed Fedora system. At the very top of this file, insert this crypto mount command. Paste the UUID of the encrypted partition you copied earlier here. Make sure to remove the dashes from the UUID. Grub expects the UUID in a dashless format, otherwise the crypto mount command may fail. Save the file and exit. Next, you will need to enable the necessary grub modules to support encrypted disks. So open the default grub configuration file inside your installed Fedora system. Add this line to specify the grub preload modules. These modules allow grub to handle LUKS encrypted partitions at boot time. CryptoDisk provides basic encryption support, and LUKS adds compatibility for LUKS volumes. And also add this line. This ensures that grub is aware that it needs to unlock encrypted disks during boot. Now, save the file and exit. Regenerate the grub configuration to apply all the updates. At this point, the post-installation setup for enabling full disk encryption with LUKS is complete. You can now safely reboot your system. Upon reboot, you will be prompted to enter your passphrase twice. The first prompt appears before the grub menu loads, as shown here. Enter your LUKS passphrase. Please note that nothing will appear on the screen while you type. No asterisks or characters will be shown. This is completely normal. Just type the passphrase correctly and press enter. After a brief pause, which may take up to 15 seconds depending on your processor, the second passphrase prompt will appear. This occurs just before the root file system is mounted by the operating system. Later in this video, I will show you how to bypass the second passphrase prompt using either a keyfile or TPM for a more seamless boot experience. Once both passphrases have been entered correctly, the final stage of the Fedora installation will begin. You will be prompted to create a username, set your password, and configure other preferences. I will go ahead and quickly complete these settings. Once finished, you will be logged into Fedora Workstation 42, featuring the brand new GNOME 48 desktop environment. Now open the terminal. I will increase the font size so the text is easier to read. I will also switch to a bright color scheme to improve visibility. The first thing I'll do is change the host name of the system. I am setting it to Fedora, but feel free to set it to whatever you like. After changing the host name, close the terminal and reopen it to make sure the new host name is applied. As you can see, the host name has been updated successfully. By default, Fedora enables a feature called the hidden grub menu. Since we're setting up Fedora with snapshot and rollback support, we want the grub menu to always be visible. This way, we can easily boot into snapshots when needed. So let's disable the hidden grub menu feature. Here you can see that menu auto hide is currently enabled. I will go ahead and disable it. Now, if we check again, you can see that the menu auto hide feature has been successfully disabled. Next, let's inspect the Btrfs file system setup. This command displays information about your mounted Btrfs file systems, including the device path, label, UUID, and total size. It's a good way to confirm that your root file system is using Btrfs as intended. Now, let's check the layout of your disk and partitions by running this command. You should see output something similar to this. Finally, let's list the Btrfs subvolumes to confirm the setup. You should see output like this. Each subvolume helps isolate different parts of the system, making snapshots and rollbacks more flexible. The last subvolume, var/lib/machines, is automatically created by systemd. It is used for managing lightweight containers through tools like systemd nspawn or portable services. Even if you're not using containers now, having a separate subvolume for this directory improves system organization and makes future container management much easier. Now, let's update the system to ensure everything is up to date. The update is now complete. Now, reboot your machine to apply all changes. To make sure important user data is preserved when rolling back snapper snapshots of the home subvolume, it's a good practice to move certain application directories into their own dedicated Btrfs subvolumes. This way, they won't be affected by Snapper's undo change or rollback operations. As an example, I'm going to create a separate Btrfs subvolume for Firefox's configuration directory .mozilla. This ensures that Firefox settings, bookmarks, and other user data are protected from rollbacks affecting the main home subvolume. However, since the .mozilla directory already exists, I cannot simply create a new subvolume with the same name. To work around this, I'll first rename the existing directory. Now that the original .mozilla directory has been renamed, I can safely create a new subvolume. Let's check to confirm that the new .mozilla directory has been created. You will also notice that the directory is owned by the root user. We want the currently logged in user to own this directory, so we'll need to correct its ownership. Run this command to recursively change ownership of all files and directories inside your home directory, including hidden ones. Now, let's verify that the ownership of .mozilla has been updated. Next, I'll copy the contents of the old .mozilla directory into the new .mozilla sub volume. Now that all the files have been copied, it's safe to delete the old directory. Since we modified the file system structure, it's a good idea to restore SELinux context, especially if you are running Fedora with SELinux enabled. Finally, let's list all Btrfs subvolumes to confirm that .mozilla now exists as its own subvolume. In this demo, I've only created a subvolume for .mozilla to show you the basic steps. Depending on your workflow and needs, you might also want to create additional subvolumes for other important application directories. Here's a table with some common examples you may want to consider. Creating separate subvolumes for these directories can help protect critical configuration and security-related data during system rollbacks. When using full disk encryption with Fedora, the grub bootloader prompts you to unlock the boot partition by entering your LUKS passphrase. However, this decryption step is not passed to the init RAM FS stage, which means you will be asked to enter the same passphrase again to unlock the root partition. This can be inconvenient. To streamline the boot process, you can configure automatic unlocking using either a keyfile or TPM2. In this video, I will demonstrate both methods so that you can choose the one that best fits your system. A keyfile works on all systems, regardless of whether Secure Boot is enabled or disabled. On the other hand, using TPM2 for automatic unlocking requires that your machine has a TPM chip and that Secure Boot is enabled. This section will walk you through bypassing the second LUKS passphrase prompt using a keyfile. Advantages of using a keyfile is it works on virtually all systems, regardless of whether Secure Boot is enabled. It is simpler to set up and does not depend on specific hardware. It also gives you more control and flexibility in how and where the key is stored. The disadvantages are the keyfile is stored on disk, so if your system is compromised, an attacker who gains root access could potentially extract the keyfile. And if someone copies the key file along with your disk, they could unlock the encrypted volume without needing the passphrase. So if your system does not have TPM2 or you prefer a simple setup, using a key file is a good choice. If you do have TPM2 and want the highest level of security, then TPM2-based unlocking is the recommended method. I have added a video chapter timeline for easy navigation. Simply hover your mouse over the YouTube progress bar and click on the next section. So let us begin with the keyfile method. First, switch to the superuser account. Next, run this command. This command will display your block devices and their properties. You need to identify the UUID of your LUKS encrypted device. Look for the long string that begins with LUKS-. This is your LUKS UUID, and it uniquely identifies the encrypted volume. You will need this UUID throughout this section, so copy it. Now create a directory for storing keyfile. This directory is used by systemd crypt setup to automatically load key files during boot. If a matching key file is found here, the system will use it to unlock the encrypted volume without prompting the user. Now generate a 4 KB random key file using this command. This command creates a binary key file filled with random data, which will be used to unlock your LUKS volume. Be sure to replace the UUID with the one you copied earlier. Next, verify that the file has been created. You now need to restrict access to the key file to ensure it is secure. So run this command. Check again to confirm that the permissions have been updated. You should see that the file is readable only by the root user. Next, run this command to add the key to an available LUKS key slot. Paste the UUID you copied earlier. Be very careful with the UUID. If it is incorrect, your system may fail to boot. You will be prompted to enter your current LUKS passphrase to authorize the addition. To verify that the key was added correctly, run this command. Check that a second key slot is now in use with pbkdf2 as the key derivation function, and an iteration count of 500,000. Now that the key has been added, you need to include it in your initram fs so that it is available during early boot. So create a new configuration file to include the key file in the initram fs. Add this line. Replace the UUID as needed. Save the file and exit the editor. Now rebuild the initram fs. Finally, reboot your system to apply the changes. Enter your first LUKS passphrase, which will be prompted before the grub menu is displayed. You should not see the second passphrase prompt. If everything is configured correctly, the system will proceed directly to the login screen. You have now successfully configured automatic unlocking of your root partition using a keyfile. In this section, I will show you how to bypass the second LUKS passphrase prompt using TPM2, also known as the Trusted Platform module. I have reverted all changes made in the previous section where we used a keyfile to bypass the second passphrase. This ensures that we are starting from a clean state. If you plan to use the TPM2 method, you will be following a fresh setup without any leftover configuration from the keyfile approach. For this method to work, your computer must have a TPM2 chip and secure boot must be enabled. The advantages of using TPM2 over a keyfile are: it is more secure because the decryption key is stored inside the TPM chip, not on disk, making it much harder for attackers to steal, even if they gain access to your system. It provides tamper protection, meaning TPM2 checks if your system has been modified before releasing the key. So if someone tampers with your bootloader or kernel, auto unlock won't work. There is no file to manage. You don't need to store or back up a separate key file, which makes the setup cleaner and easier to maintain. And finally, it is safer against disk cloning. If someone copies your entire disk, they still can't unlock it without the same TPM chip on your motherboard. The disadvantages of using TPM2 are: it is tied to your hardware, meaning if your TPM chip fails, the auto unlock doesn't work. But don't worry, if the TPM chip fails, you can still unlock the disk manually using your LUKS passphrase. And it is not portable. Unlike a key file that you can move to a USB stick or another system, TPM2 based unlocking only works on the same computer. You can't easily transfer it to another one. So if you have a TPM2 chip and want the highest level of security, this is the recommended method. First, switch to the super user account. Now verify that secure boot is enabled. You should see a message confirming that secure boot is active. Next, check if your system supports TPM2. If your system supports TPM2, you will see output showing the device path such as /dev/tpmrm0 along with the driver information. Now that you have verified that both TPM2 and secure boot are available, we can continue with the configuration. Next, run this command. This command will display your blocked devices and their properties. Look for the device that contains your LUKS encrypted volume. You will see a long name starting with LUKS- followed by a UUID. This is your LUKS UUID, and it uniquely identifies the encrypted volume. Copy it. You will need it in the next few steps. Now, enroll your TPM2 device with the encrypted volume. Replace the UUID in the command with the one you copied. Be very careful to use the correct UUID. If you use the wrong one, your system might fail to boot. You will be prompted to enter LUKS passphrase, enter the existing LUKS passphrase that you created during installation. To confirm that the TPM2 key has been successfully added, run this command. You should see an output showing two slots, one for the original password and one for TPM2. This confirms that the TPM2 slot has been successfully created. Next, you need to add the TPM device path to your kernel boot options, so run this command. To confirm that the boot options were updated correctly, run this command. Look for the RD LUKS options entry. It should now include the TPM2 device path. You also need to update the cryptab file so that the system knows to use TPM2 during boot. So open the cryptab file and append this option to the end. Save the file and exit. Next, you need to ensure that the TPM2 module is included in your system's init RAM FS. This ensures the TPM is available early in the boot process. So create a new configuration file to include TPM2 module. Add this line. Save the file and exit. Now regenerate the grub configuration. And rebuild the init RAM FS image. Once everything is complete, reboot your system. Enter your LUKS passphrase. You should no longer see the second passphrase prompt, and if everything has been configured correctly, the system will continue booting and take you directly to the login screen. You have now successfully set up automatic unlocking of your encrypted root partition using TPM2. Next, let's enable snapshot and rollback support on Fedora. To set up a robust snapshot and rollback system, we will first install a few important packages. Snapper manages Btrfs snapshots. It allows you to automatically create, view, and restore snapshots for system rollback and recovery. Now, let's set up automatic snapshot creation through DNF. Snapper integrates with DNF using a custom actions file. This file tells DNF to automatically create snapshots before and after any package operations like installs or upgrades. To create this actions file, paste this code into your terminal. I will include the code in the description and on my website for easy copy pasting. Press enter to apply it. Once done, verify that the file was created correctly. Next, we need to create Snapper configurations for the root and home file systems. First, create the configuration for root. This command tells Snapper to start managing snapshots for the system root directory. Then, create the configuration for your home directory. This sets up Snapper to manage snapshots for your personal files in /home. Confirm that both configurations have been successfully created. Next, we need to restore the correct SE/Linux context for the .snapshots directories. This ensures that SE/Linux labels are properly applied, which is important for system security and Snapper's functionality. Verify that the SE/Linux labels are set correctly. Next, we'll grant the user access to Snapper and sync the file ACLs for both the root and home configurations. First, I'll configure it for the root volume. Then I'll apply the same settings to the home volume. This allows your user account to manage snapshots without needing root privileges and ensures file permissions are handled correctly. Next, list the subvolumes. You will now see new .snapshots subvolumes created for root and home. Before moving forward, let's optimize system performance. We need to prevent the system indexer from scanning the .snapshots directories. So open the configuration file. And add this line. Save and exit. Now list the root snapshots. Then list the home snapshots. At this point, no snapshots exist yet. They'll be created automatically when you install, update, or remove packages, or when you create them manually. Now let's install and configure grub-btrfs. This tool allows grub to detect and list your Btrfs snapshots at boot, letting you boot into a previous system state if needed. First, clone the repository. Change into the directory. Open the config file for editing. We need to apply a few Fedora specific adjustments. Uncomment this line. This enables overlay FS support, allowing snapshots to boot into a temporary overlay layer. Uncomment this line. Fedora stores grub files in grub2, not grub, so this change is needed. Then uncomment this line. Again, Fedora uses grub2 to regenerate grub menus. And finally, uncomment this line. This ensures grub script syntax is validated correctly when updating the grub configuration in Fedora. Save and exit the editor. Now install grub-btrfs. You might see a no snapshots found message. That's normal because we haven't created any snapshots yet. Next, enable and start the grub-btrfs monitoring service. This daemon watches for new snapshots and updates the grub boot menu automatically when needed. Your grub-btrfs setup is now finished. You can now safely remove the cloned directory. And with that, your system is now fully set up for snapshot and rollback support. Snapper is now ready to manage your system and home snapshots, and Grub will automatically detect them, allowing easy restoration if anything goes wrong. Your system is now snapshot ready. Now that everything is set up, you can enable automatic timeline snapshots. With this feature enabled, Snapper automatically creates a snapshot every hour. And once a day, the timeline cleanup algorithm removes older snapshots based on your configuration settings. By default, timeline snapshots are enabled for both the root and home configurations. However, it's recommended to keep it enabled only for the root and disable it for the home volume to avoid excessive snapshot clutter. So enable timeline snapshots. This timer schedules periodic snapshots of your file system, allowing you to roll back to previous states if needed. Similarly, enable cleanup timer. This timer regularly deletes old snapshots based on your Snapper cleanup configuration to free up disk space. That's it. From now on, Snapper will automatically create one snapshot every hour and clean them up daily according to the timeline settings. As you can see, a new timeline snapshot for the system root has been automatically generated after an hour. To showcase Snapper's capabilities and highlight how useful it can be in real-world scenarios, I ran a series of practical tests. I strongly recommend trying out these tests yourself. They'll give you a much clearer idea of how Snapper can help you recover from system-breaking changes like misconfigured updates or accidental deletions. I will include the link in the description. And that brings us to the end of this guide. If you found this helpful, drop a like and let me know your thoughts in the comments below. Thanks for watching, and I'll catch you in the next video. Until then, take care, stay curious, and happy exploring.